Okay, continuing whatever that we already know about the multiple dosing. For first, we will talk about IV bolus. Then, second, we will talk about extravascular. Okay, and again, whatever is here in this slides or in this class. So it's just only a review of the multiple dosing kinetic for IV bolus and extravascular. Okay. Again, when we were talking about a single dose, we were interested mainly about the dose. Then we talked about kinetic, and here we are interested also in the dosing interval, which we called it tau. Okay, we had already explained and reviewed the kinetic of a single dose whatsoever, if we're talking about IV bolus or intravascular or extravascular. And here we will talk about multiple doses and how we can use the kinetic parameters of a single dose to extrapolate it to multiple doses according to multiple assumptions that we have. And if we're talking about IV bolus, if we remember, this is our dose if we are talking about CB versus time on a rectilinear profile. And then we explained the idea of multiple doses, but independent doses, in which if we are talking about CB node here, then we have the first dose, and then let's say that we started here, this is the second dose. Okay, so this is CB versus time on a rectilinear profile because we have exponential, and this is CB node for the second dose, and this is CB node for the first dose. This is the first, this is the second. And as again, this is the same example that we explained before, the CB node for both of them are the same because we give enough time for the drug to be eliminated completely. If you are talking about theoretical time needed for the drug to be completely eliminated is infinity. If we're talking about practical, so we are talking about more than 5 half-lives, which we usually said that it's 5 to 7 half-lives. And in this case, which is again, we give an enough time for the drug to be washed out. In this case, it's actually a multiple dose, but at its independent multiple doses, we still use the kinetic of a single dose for both of them to determine any of the details or parameters that we are interested in. Okay, for multiple doses, and the multiple doses we are talking about dependent multiple doses, in which the time between different doses, so let's say this is the first dose and this is the second dose on the y-axis, the time between the first dose and the second dose or the subsequent dose is not enough for the drug to be completely eliminated, so it will be less than infinity in theory or less than 5 half-lives in practice. Okay, and this is one of the examples I mentioned in which the concentration the initial concentration for each dose, if we consider this as our first dose, second dose, third, and let's say this is infinity or steady state. Okay, the concentration, which is a start concentration, or let's call it CB node for each dose, which is the same as CB max of each dose, according to what we know, is increasing as the dose is increasing, and CB end or the CB minimum of that dose is again increasing in incrementals, in small increments, just say increments, no increments for each and every dose. And we notice that the concentration eliminated with time is start to be at time infinity or at steady state, similar to the end concentration that we have. So as we talked about before, the output start to be equal to the input, which is the definition of our steady state. So whatever is happening according to the dependent multiple doses, in which the concentration, let's draw our profile versus time. Let's talk about a rectilinear. So we are talking about until we reach the steady state. Okay, so the initial concentration for each dose is increasing with more doses. Okay, and the minimum concentration or the end concentration is also increasing with more doses or the subsequent doses. Okay, for this is before reaching the steady state. Okay, and for the steady state, we know that the Cmax or of the doses is equal for each and every dose at steady state, and for the C minimum is also the same for all the doses at steady state. And we know that this happens at time infinity in theory, okay? But we mentioned that this happens at time that is more than half-life usually in a practice, okay? And this is what I mentioned either in this point or in the second point here, okay? We have a principle that is called superposition principle or the overlaying principle, in which the early doses kinetic is not affected by the pharmacokinetic of the subsequent doses, with our assumption that we are still talking about first order kinetic. And why this principle is very important. So again, we are talking about linear kinetic, and accordingly the kinetic of each and every dose is not affected by previous or subsequent doses kinetic. And this is very important because we can use the kinetic that we already know from a single dose to determine or extrapolate whatever we need to know about the multiple doses. We have some exceptions, such as if the pathophysiology of the patient is changing, because if the pathophysiology is changing, so let's say the volume distribution is changing, the clearance is changing, saturation, which is an example of non-linear kinetic, induction and inhibition, and also an example of non-linear kinetic, which is the last chapter that we explained in basic kinetic, which is in which we don't have linear kinetic, or example of the exception of the linear kinetic. According to the superposition principle, we were able to determine what we called it dust ratio, or in other references called accumulation factor, in which is R equal to 1 minus the exponent of minus n k tau, in which n is the nth dose that we are talking about, k is the elimination rate constant, which is first order, okay, and tau is the dosing interval, okay, over 1 minus the exponent of minus k over tau. And this ratio was used to have a relationship between the kinetic of a first dose with multiple doses, and then we entered this ratio into the mean model equation of a single dose that we already know it, either in an amount or concentration, but the difference that the equations start to be for the nth dose. And this is one of the important difference between a single dose and multiple doses equations, in which we are talking in the multiple dose equation for the nth dose. So for certain dose. So if we are talking about 1, then this is our dose. If we are talking about 3, so this is only the profile that we are talking about, not the whole profile as in the model equation of the single dose. So we just enter the dust ratio to the equation that we already know. Okay, we have an xp node multiplied to the exponent term, or CB naught multiplied to the exponent term, and we just add the dust ratio or the accumulation factor. And I keep alerting you all the time to not confuse yourself with tau and T and the equation. And if we remember, tau again, it's the dosing interval, right? So in each and every dose, this is a tau, and we mentioned that tau could be changing, and we will see in the adjustment of different dosing regimen or therapeutic regimen, you may need to change tau with time according to the results of the concentration that you have. And we have T, which is the time since the administration of the nth dose. So if I'm talking about n equal 4, tau is equal to 6, and the time is equal to 2, let's say hours. Okay, so we have 1, 2, 3, and 4. So this is our dose that we are talking about. So the profile that we are interested in is this. Okay, tau, which is the dosing interval that we are talking about, is 6 hours. Okay, this is this is the nth fourth dose. Okay, and the time is 2 hours, which is the definition of the 2 hours since the administration of the fourth dose in this case, which means that if I'm talking about 2 hours since the administration of this dose, which means that I'm talking about the concentration after 2 hours of the administration of this dose. So after the start, we are having 2 hours, then this is the concentration I'm interested in. So I can determine the concentration as n equal 4 at time equal 2, and this is would be the concentration I'm interested in. So all the time I was like, be careful when you are talking about the concentration because it's for nth dose, not the whole profile, and the time is since the nth dose administration. Okay, and then after that we had, if you remember our game in this case, we had concentration and at certain time equals CB naught multiplied to the dust ratio in k tau over 1 minus k tau E minus k with time. And we had either changing in n, changes in n, or in the time, or both of them. And we started with this, okay, in which the n, which is the nth dose, could be either 1 or infinity. This is similar to the single 1 dose, okay, and this is what we call it steady state. Okay, and in each time what is changing is the nth dose, or changing in this n in the equation. If we are talking about the time, which is again since nth dose administration, then this would be the lowest time would be 0, and the highest time would be tau for each dose, right? If we go back to our drawing here, let's change, no, it's not clear. What's this? For each dose, the lowest time that we have, if the total is tau, the lowest time that we have is 0, The highest time that we have is tau. And we can have time in between. So in this case, we have tau equals 6 hours. So for each dose, the time for each dose could be ranging from 0, which is the lowest, to tau, which is 6 hours. Right? This is the range of the time. And for our case, for 0 would be for each dose called that CB node for that dose, which is the maximum of that nth dose, and tau would be CB minimum of that dose. This is the same as CB peak for nth dose, and this is the same of CB trough for that nth dose. And this is just the way or the diagram or timeline for you to go for each and every one of those changes, either in n or the time or both of them. And this is what is mentioned in all of the slides from now on. So let's start with the first one, which is in n equal 1. We said that n could be 1 or infinity. So starting with 1, when n equal 1, then we need to substitute this with 1. Then accordingly, we can strike out this term with this term, right? Then you have the equation of CB at certain time equals CB node multiplied to the exponent of minus k over time, which is the same of the model equation that you know for a single dose. And for sure, it should be the same, okay? When the n equal infinity, and notice that we didn't change anything related to the time. So when n equal infinity, which means that I need to substitute n with infinity, right? So this would be 0. Then the concentration at infinity, certain time, would be CB node multiplied to 1 over the term that we have here and the last exponent term, okay? This is whatsoever the time that we have. So if we are talking about the time, again, the time for each and nth dose could be 0 or tau. At 0, we are talking about the CB max or the peak, which means that I need to substitute the time here with 0. And when you substitute the time with 0, it means that this term would be 1. Then accordingly, the CB max at any time, no, it's not max at any time. This is, we need to correct this. This is the CB max for nth dose. Okay? This is the maximum or peak for nth dose. Okay? For the time equal tau, okay, again, this would be minimum at nth dose or the trough at nth dose. We need to just substitute this with tau, which is the minimum concentration at nth dose, whatsoever the nth dose that we are talking about. And for sure, as we are interested in the this stage, which is our what? Steady state, then we need to have at steady state, we know that if we are talking about at steady state, then n equal infinity, okay? And we are interested about either the time is equal 0 or the time equal tau. So we are talking about steady state, either CB max at steady state or CB minimum at a steady state. And again, if you go through the steps, if you have this, by the way, in here, some of the, it's not there, but you should have it in your PDF, okay? So if you substitute n equal infinity, which is this, okay? And we know that we will lose this. And then either the time equals 0, which this would be equal to 1, or the time equal tau, then accordingly, this would be changing to tau. Okay, so again, this is explained here. When n is equal steady state, then this is our equation. And if we are talking about the maximum at steady state or infinity, we will have CB naught over 1 minus the exponent of minus k multiplied to the tau. Minimum would be the same, but with the exponent term multiplied to the tau rather than time, which would be equal to CB naught, now CB max infinity, which is all that, right? Which is this, multiplied to minus k with time, which is common sense, because at each dose at the steady state, this concentration would be this concentration multiplied to the exponent term that caused this decrease, right? Which be multiplied with the exponent minus k multiplied to the time at this point, which is what? Tau, which is again the same concept that you know, but just we are adding it in the terms of multiple doses. Okay, and this is what we are explaining the whole profile that I already explained to you in the previous one that I draw manually. Okay. Again, in the maximum plasma concentration at steady state, so again, we are talking about time equals 0 at steady state, which is n equal infinity. We have this equation in which we know that it depends on the CB node, which is equal to X node over VD, and depends on the elimination rate constant and tau. Okay? So it depends on the frequency and the dose of the drug taken. And if we go here, we know that increasing the dose for sure would affect by increasing, if I increase the dose, by default, I'm increasing the overall plasma concentration. Okay? And if I take the drug more frequently, so the frequency is higher or larger, it means that the tau, the time between different doses, is less, which means that I'm giving less time for my drug to be eliminated. So by default, this would increase my maximum concentration at steady state. And this is the same if we are talking about the maximum concentration for any dose. And it's also similar to the concentration minimum at steady state, because the equation that we have is here, which is the same. So more frequent doses would cause a higher trough plasma concentration because it's going under the same principle. Okay? And here, percentage of a steady state, reaching certain percentage of steady state, see of the duration of the drug administration. If we are giving less frequent drug, which means the duration of the administration is more. No, if the, 1 second. So we are talking here about the drug administration, if it's covering how many half-lives, if it's increasing the half-life that in the duration of that time of the drug administration, then the percentage of reaching the steady state is more. Okay, and this is what we already know. And again, for practice or in practice, we know that we need at least 5 half-lives to reach more than 95 of the drug. And we know that if you are if you want to be more restricted, so 7 half-lives to be more than 99% of the drug 99% of the steady state, the final steady state that you have. And again, this is mathematically measured in the fraction of the steady state that we will see in a minute. Okay? And for sure, the different time to reach the steady state, or the time to reach the steady state, or time to reach certain fraction of a steady state is different according to different drugs, because we are talking, and again, it's different with different individuals and different with different diseases, but it's different for different drugs again, because we are talking about different half-lives. So if we are talking about different half-lives, then the time to reach certain fraction of the steady state or the practical steady state is different. Okay? The time to reach the steady state, if we're talking in general or even certain fraction of the steady state, depends only on K or half-life, which is similar to whatever you know already. So it won't be affected by taking different doses or different taus. So that's why if we want to reach that steady state directly, we usually go under taking, or we need to take a loading dose to reach the concentration directly. Okay? Steady state concentration are commonly used in practice, and we will see this in our calculation when we are entering the stage or the part of this course that is related to the certain groups of the drug. We either increase the dose, as I mentioned earlier, without changing tau, okay, or we can use the same dose, but we decrease our tau, okay. It depends on the case that we are talking about, and sometimes we could change both of them to get the concentration that we are interested in. Okay? And again, for sure, the time to reach the steady state is not changing, not in here and not in here. Okay? The average steady state concentration, which again, it's something that you already know, that it's a concentration between the maximum and minimum concentration at a steady state, and it's not the geometric or the arithmetic mean, so you don't just have the summation of both of them over 2. It's not. It's actually a concentration between both the maximum and minimum, and it's usually used in clinical practice to define if we are within the range that we want. And how we determine it, as again, we have some distortion here, from 0 to tau, concentration at infinity time over tau. So the average steady state concentration is equal the integration of the concentration at steady state from 0 to tau over tau. Okay, and it's usually the desired or targeted concentration. And why is that? Because it's easier for us to measure it in clinical practice. And when we go under the integration for the steady state, average steady state concentration, we can find that it's equal, because this is equal dose over K multiplied to VD, dose K VD multiplied to the tau, and this alone is called dosing interval. We know that it depends, the average steady state concentration, it depends on the dose, administered dose, elimination rate constant, volume distribution, or total or systemic clearance, and dosing interval. And because we are usually in our cases not changing the dose, and until now for sure we're not changing the dose, and those terms are constant because we are talking about linear kinetic, then accordingly the average steady state concentration is mainly dependent on tau, because the dose is constant. Okay, or in other words, I can, by changing the dosing interval, I can determine the target concentration by knowing those kind of parameters. Okay. And we mentioned also, according to this, that the area under the curve from 0 to tau at the steady state is equivalent, according to the math and what we know, of the area under the curve from 0 to infinity of a single dose. So again, area under the curve from 0 to tau at steady state is equivalent to the area under the curve from 0 to infinity. And this what we can find in math, or by using math, because average steady state concentration is equal 0 to infinity for a single dose over tau, which is equal 0 to infinity over tau. Okay, again, because this is equal x naught over vd multiplied to k, okay, which is this, multiplied to tau, which is this. Okay, so accordingly, again, this area under the curve is equivalent to this area under the curve. And we said this is very important in practice because we can use just a single dose and determine the parameters that we know, because we know the dose, okay? We can determine K, we can determine VD, and then by just knowing tau or changing tau, I can determine the average steady state concentration, which is the targeted concentration between the steady state concentration minimum and maximum. Okay? We have again the factors affecting is the clearance, K, VD, dose, and tau. Okay? So changing of any of those parameters would affect at the end the steady state concentration. Okay, so let's talk about those factors. So if I want to change the drug clearance, which is the total clearance, again, we know that this could be either related to the renal excretion or hepatic metabolism or the metabolism in general. So any factor affecting those would affect the final average steady state. And we know from here, by decreasing the clearance, okay, decreasing the clearance, the average steady state would increase. Why? Because again, you are decreasing the elimination either by excretion or by metabolism. So the average steady state would be changing. What would be the effect of the volume of distribution? Again, all the time we were assuming that K, VD, total clearance, and also the dose, this is not changing, and we were assuming that those factors are not changing. But what if they were changing, or what if less volume distribution? What would be the effect on the average steady state? And this is those are the examples of that. So if the body water compartment is changing, okay, especially for the drug that is going through those aqueous compartment, then the increase in the body water, okay, or fluid, or decrease in the body water or fluid would affect the overall volume distribution. And again, why I'm saying that primarily for the drug distributing in those compartments, we will see this in the distribution of the drugs, if it's hydrophilic or lipophilic, and we know the distribution would be different. But we know if the drug is primarily distributing in the hydrophilic compartment or watery aqueous compartment, then increasing the body water, such as in renal failure, would increase the volume distribution. So accordingly, if this increases the volume distribution, then the total average steady state would decrease, and the opposite if we are talking about decreasing the body water, as in dehydration or burns. Okay, if we remember the accumulation factor or the R, capital R, we know that we can define this or have it by 3 different ways, and it's all related to something at steady state compared to a single dose, and the term of the accumulation is equal to this term. And whatever the way that you are doing it, such as maximum at steady state, maximum for the first dose, minimum at steady state over the minimum of the first dose, we will still have the same term, and we talked about the effect of the number of half-lives or dosing interval or changing the frequency of the drug administration on the drug accumulation. And just to remind ourselves, if the number of the half-lives, which was represented as capital N in dosing interval, is increasing, which means that tau is longer. It means, according to we mentioned, if you go down, it's the tau is longer, which means that the frequency of the drug administration is less, which means that I'm giving more time for my drug to be eliminated, which means that the CB max and CB minimum for each dose in its steady state is less, which means that the drug accumulation is decreasing. Okay? And we know the relationship between the number of half-lives, okay, in tau, and we can add it to the term of any of the equations that we have. We know that this principle is the opposite of what we have for the fluctuation. And for the fluctuation definition, we know it's the relationship of whatever is happening at steady state between either maximum and minimum at steady state, or maximum at steady state with the average steady state concentration. And we know even the number-wise, the quantity of, or the value, let's say the value of the number is different, but the principle is still the same, which means that if the number of half-lives in tau is increasing, so tau is longer, or the frequency is less, we said that the accumulation would be less, but the fluctuation is more. And we know those details already. As I mentioned, we can determine the certain fraction of a steady state. What is the fraction if we know the number of doses or nth dose taken, K, which is the elimination rate constant, and tau, which is the dosing interval. We can determine the time to reach certain fraction of the steady state. And from the equation, and of course, this is just a rearrangement of this for certain time. And we know that in this equation, that the time to reach certain fraction of the steady state is only dependent on the half-life, or in other words, K. Okay? And we know this already. Okay? And this slide, slide 2 and 3, we know that those are things that you already know, and we have simulation sheets that I already uploaded on your e-learning to play around with them. And if you change one of those, either K and the effect of those terms, or the tau, decreasing tau, or doubling the dose. Okay? So let's go with the first one, and you will do the other two by yourself. But again, you can do it just by common sense, or you can do it by using the equations that we have here. So let's start with this. If we decrease K, it means that the half-life would increase, because 0.693 over K equals half-life, right? So if this is decreasing, this is by default is increasing. Okay? So this is the first one. What about C max at steady state and C minimum at steady state? You can use the common sense. If K is decreasing, which means that the elimination rate constant is decreasing, what would be the effect on the profile, and accordingly what would happen if we are not changing anything other than K? Okay, or you can just go to the equation here. If it's in the exponent term and you are decreasing K, okay, so the whole thing is increasing as magnitude. So the same number over less number would be higher, and the same thing would be in here, so would increase the value of maximum and minimum concentration. If we are talking about the average steady state concentration, this would be decreasing, so the average steady state concentration would be increasing. If we are talking about the ratio of both of them, because we have, if we are having CB max over CB minimum, we will have, let's remove this, we will have this over this, which means I will have E K over tau. And this is, if you remember, equal to one thing, which is what? Which one of them, of the terms that we are just mentioned in a minute? It's what? It's the same as fluctuation, okay? So as k is in this term, so if it's decreasing, it means that the whole term is increasing, so the ratio would be 1 over less number would be decreasing. Okay? Again, بإمكانك تتعامل مع الموضوع common sense وتشوف إذا أنا قللت أو زدت كي شو راح يصير عندي بالبروفايل إذا ما غيرت أي إشي تاني، أو تتعامل مع الموضوع as math بحت بما أنه عندك ال equations. And you can again play around with the simulation sheets that I have online for on your e-learning for IV bolus multiple doses, or we have it too for for extravascular and multiple doses route of administration. Okay, and you can do the same thing for tau and increasing the dose. For the multiple dosing extravascular administration kinetic, first of all, you need to remind yourself that each dose, if we are talking about just one dose, let me have another slide because it's not playing well with me. So if we are talking about one dose, as we just mentioned in the previous review, that we are starting at 0, we are having maximum, and then we go back to the least that we can have. If we are talking about single dose, and in theory, then we reach time infinity to a concentration that is equal to 0 again. So we start at 0. And then we end at 0 if we are reaching the infinity. So this is the only difference as, let's say, graphical wise with the IV bolus. That's why for each dose we start with 0, then maximum, then the minimum for each dose. Again, maximum and minimum for each dose. So the maximum, one of the differences, it happens at T max for each nth dose, not at the time equals 0. But still, the concept is the same. At tau, the tau ranges between, or the time of each dose is ranges between 0 to tau, okay? Still, this is the administration of the dose. Tau is the CB minimum of that dose, and the maximum would be at time equal Tmax, okay? Again, we still have the same thing. We have time to reach the steady state as the concentration maximum increase with taking more doses, and the minimum concentration also increase with taking minimum subsequent doses until we reach to the steady state in which we are having similar minimum concentration, the same minimum concentration, and the same maximum concentration, okay? For the extravascular multiple doses, we have the same equation for the single dose, in which we have the constant, one exponent related to the elimination and another exponent related to absorption, but we added dust ratio that is related to elimination, to the elimination exponent term, and we are having also dust ratio that is related to absorption, and we add it to the absorption exponent term. And the same thing, tau is the dosing interval. The concentration equations start to be for nth dose at certain time from that nth dose, and again the time ranges between 0 to tau. Okay. We were able to determine a steady state concentration in which we just substitute n as infinity. So it started to be 1 instead of this term in each one of those terms. And if we did rearrangement of that, we had a shorter equation for this equation. And no. This is... Yes, this is the steady state at certain time, not at Tmax, okay? When we had Tmax, we mentioned that Tmax only at steady state, which was more complicated when we compare it to Tmax for a single dose, and this is for sure obvious because we are talking about multiple doses, but still it depends on Ka and K only, and it's independent on the dose. Okay, if we want to determine steady state average, steady state concentration, this would have the same concept, 0 to infinity, 0 to tau at infinity over tau, okay, which is for the at steady state concentration, 0 to tau, it's the same steady state concentration dt over tau. If we do the differentiation, we will have it equal to fraction multiplied to the dose over k vd multiplied to the tau, and this was also the same as the integration of 0 to infinity of the single dose. That's why we have this as total area under the curve over tau, and the only difference is F, which is the absolute bioavailability that we talked about earlier. And this is for sure, again, something that we should know because we are talking about the multiple doses of extravascular, so not the whole dose would reach the systemic circulation. And the same concept of what we said in IV bolus as this, the average steady state concentration is equal to the integration of 0 to tau at steady state, and it's similar to this the integration of the first dose over tau. That's why we use a single dose kinetic or single dose BK parameters to get information about, again, the fraction dose K and VD, and by changing only tau, we can determine the steady state average steady state concentration. And by this,